In section 5.3, we're going to go through graphing polynomials. In this section, we're mainly going to focus on cubics, and as you've seen before, cubic functions kind of look like a squiggly line like this. And some new vocab that we're going to learn here is a relative maximum or minimum. So, a relative maximum is the value of a function at an up-down turning point. So looking at this function, if I follow it along with my pencil, that point where I stop going up and start trending down, that red dot right there is called a relative max. Similarly, a relative minimum is where I have a down-up turning point, where I stop going down and then I start trending up. I call these relative max and relative min because, as you can kind of see here in this graph, that relative maximum, or that red dot at the top there, is not the highest point that this graph can go. As you can see, it's trending up like towards infinity. Same thing with the relative min. That's not my lowest point. I still can go down towards infinity, but those points are still important and they're going to matter, as you're going to see in the last example that we do today. So again, we call them relative max, relative min for these types of problems. You find them the same exact way as you would a maximum or minimum in your graphing calculator by doing the upper and lower bound. So it's essentially kind of the same thing, but with like a little difference. So let's go through how you would graph like a cubic function. So here I have f of x equals x plus 1 times x minus 2 times x minus 3. Now this is in factored form, which is nice because I can already see where all of my zeros are and I can plot those. On a test, I'll mainly be checking for the key features, so to see that you have your zeros plotted and your relative max and min in the correct ballpark. So first, let's start out by graphing my zeros. If I have x plus 1 as a factor, that means I have a 0 at -1, +2, and +3. So from here, what I'm going to want to find is my relative max and min. And I'll do that by using my graphing calculator. I won't do that by hand. I don't even know you do that by hand, really. So if I go on my graphing calculator, I find my relative max by graphing this. I find that to be at 0.13, 6.06. And again, I'm just going to ballpark that. For my relative min, I'm at 2.54, -0.88. Again, just kind of ballparking that. I'm starting to get a little bit of a clearer picture of what this graph's going to look like. And then finally, just by looking at my graphing calculator, I can see that my end behavior is down and up. So from here, I'm going to try to connect the dots as best I can. Again, it's not going to be perfect. To the left here, I'm going down for forever. Oh, well, there we go. Going to connect my dots here. And then going to the right, going up for forever. And that would be what my graph would essentially look like. So the last thing that we're going to do today is to kind of see where a cubic function would matter in a word problem. I think it's really easy to kind of lose sight of where these problems might become important or why we even need cubic functions. But if we're dealing with a problem that has 3 different variables with it, like for example, if I want to maximize volume of a shape, know that there's 3 different things going on there: my length, my width, and my height. So that's where a cubic function would matter. So we're going to look at one example here, and then that'll be it for today. The double Crunchwrap Supreme at Taco Bell maximizes its volume while keeping the sum of its dimensions at 6 inches. Also, the length must be 1.5 times the height. Using that information, I want to figure out what should each dimension be if I want to maximize the volume of that double beef Crunchwrap. Also, would highly recommend getting that. It's one of their best menu items. Anyways, here's how I'm going to figure this out. First, in terms of volume, I'm going to keep everything in terms of x and kind of go from there to be able to graph it. So to start here, I'm going to call height my x. My length would be going this way. And instead of calling that a completely different variable of L, I look here and see length has to be 1.5 times the height. So instead of putting L in terms of x, I'm going to say that the length is 1.5 times my height, or 1.5 times x. Finally, I need to say something about the width, so I'm going to use this line here. The sum of the dimensions have to be 6 inches. What that means is that my length plus my width plus my height has to equal 6. I have kind of in terms of x values for length and height, so now I'm going to solve for width, or get that by itself. So I'll subtract x, I'll subtract 1.5x, and I'll kind of clean this up a little bit. My width in terms of x would be 6 minus parentheses x plus 1.5x. Even though this looks kind of ugly, I'm going to be able to set up an equation to graph it and then find out what my dimensions should be to maximize the volume of this Crunchwrap. So moving on here, I have kind of my important information. If I'm trying to maximize volume, let's think about what a volume equation is. Volume is your length times your width times your height. So I'm going to all write my terms of x values here. This is the equation that I'm going to end up graphing. So if I graph this, putting it into my graphing calculator, I get something that kind of looks like this. Finally, I want to maximize my volume. So I'm going to be looking for my relative maximum, which is going to be up here. When I graph this and I use my graphing calculator, I'm going to find that my relative maximum is at 1.6, 7.68. So finally, to end this video, let's talk about what those values mean. 1.6 is what my x value should be to maximize my dimensions, and that maximized volume for that Crunchwrap would be 7.68. So finally, figuring out what all of my specific dimensions should be, my height should be 1.6 inches, my length should be 1.5 times 1.6, or 2.4 inches, or my length should, and my width should be, plugging in 1.6 for x, my length should be 2 inches. So if my height is 1.6, my length is 2.4, and my width is 2 inches, that's going to maximize the volume of that Crunchwrap Supreme to be at 7.68 inches cubed. And if I wanted to double check this, remember that I wanted the sum of the dimensions to equal 6. I plug those in, I check that out, that equals 6, so I'm good to go there. And to just see what the volume would be again, length times width times height here would be 7.68, and I would be good to go.